Yes. Great. Okay. It's my pleasure to introduce Qianxiao Li, our next speaker. He is assistant professor at the Department of Mathematics in Singapore, and he's also a research scientist at the Institute of High Performance Computing in Singapore. Previously, he got his PhD from Princeton and graduated from Cambridge. Today he's talking about a dynamical systems approach to deep learning. I'm very excited about this talk. Please go ahead, Qianxiao.
All right, thank you. Thank you very much for the introduction. So I hope everyone can hear and see my screen. So today I'm going to talk about, the title is Dynamical Systems Approach to Deep Learning and Approximation Optimization, but I'm mostly going to focus on some recent results on approximation aspect. So this is this entire line of work is joint work with a lot of my colleagues in Peking University, Princeton University, and in Singapore. But today's talk, I'm going to focus on joint work with Ting Lin in Peking University and Zhou Shen in National University in Singapore. So I'm first going to start with some background and motivation, which I think a lot of the audience has already heard about a lot in this series. So I'm going to be interested in the supervised learning problem, where essentially supervised learning is about learning to make predictions. So we have a data set consisting of inputs and outputs, and there is some target oracle or ground truth function f star that we don't know, and we're trying to learn or trying to approximate. So for example, this f star will map these inputs, which are images of cats and dogs, onto their labels. Okay, so they're either words or some encoding of those labels. And the goal of supervised learning in a nutshell is to learn or approximate f star using some information from the data set, right? So how do we do this? Usually, the first step to do it is to define a hypothesis space. So what is a hypothesis space? Hypothesis space is just a collection of functions, candidate functions that serves to approximate this f star. So we're all very familiar with linear models, where you just take a linear combination of some basis functions. And hopefully, if you take many linear combinations, you will approximate f star arbitrarily well. And then, of course, there's this neural networks where you take this linear basis models a step further and consider a basis on which you have some free parameters to choose from, right? So this is an affine transformation and nonlinear activation, something that we use very often in practice. And we can adjust these parameters after we see some data, so we kind of adapt the basis to the data. So in the language of approximation theory, you can think of this as some sort of nonlinear approximation approach. And then, which is the focus of today's talk, is deep neural networks, where the difference is that now you have many of these shallow neural network modules composed together to form a very complex hypothesis space. Okay, so with a given hypothesis space, from a theoretical point of view, there's a few questions you can ask. Okay, so I will roughly group these questions into three categories. Now, the first category, which is the focus of today's talk, is that of approximation. So in a sentence, you just ask, how big is the hypothesis space? So we have some space of functions h that we guess to approximate some function f star. Then we can ask, if we were to find the best one in this entire space, how close is it to my f star? How close is it to any arbitrary f star? And this distance is the approximation error of my hypothesis space. Okay, so in the language of statistics and machine learning, sometimes you call this a bias. How much is the bias, assuming you can find the best possible approximation. Now, of course, this is not the entirety of the problem, because even if I know there is some function here that will really approximate my target well, how do I get there, right? So this is the second class of problems called optimization. That means if I start from some initial guess of a function, how can I move it close to this best approximation? And how I do it is via some optimization algorithm or control algorithm, and using some data set. Okay, so using this training data set. Now, of course, why is this two not the same? It's because my data set is finite. So there's always some sampling error. And the gap between the thing I get from my optimization and my true solution, or my best possible approximation, is measured by this generalization error. Okay, so the approximation, optimization, generalization is some three rough categories of theoretical questions you can ask, given a hypothesis space, a data set, and a target. Okay, so far, all of this applies to any hypothesis space you can imagine, right? So these are generic questions you can ask about, in fact, any supervised learning problem. So the natural question is, what's new in deep learning? And one aspect that's really new, that's relevant for this talk, is the complexity of deep learning arises from this repeated composition. Okay, it builds this hypothesis space of deep neural networks builds its complexity from repeated compositions of this simpler functions. Okay, so this shallow networks. So the goal is really, from a theoretical point of view, is to understand how these such compositions actually affects our various questions about approximation, optimization, or generalization. However, the tools that we have to study this kind of discrete composition is quite limited. So the approach I'm going to discuss today that you might be familiar with if you have attended the previous sessions is the continuum idealization, right? So we idealize a residual network, okay, on the left, which applies to this sequential transformation that Sammy also talked about before in a different application. And we take a continuum approximation and regard this layer number as a continuous variable in terms of time. So this residual network really becomes a dynamical system in continuous time. And this theta t will be a continuous time version of this weights that you have in your network. Okay, so this has been pursued, for the last couple of years in various domains, and mostly I think a lot of work focused on the optimization aspect and the control aspect. Okay, so one question one may ask is that why bother with continuum cases? So I want to motivate a little bit that in continuous time, there's a lot more tools at our disposal, right? For example, differential equations, calculus variations and control, and a lot of work on numerical analysis that can be applied to this continuous time framework. And more importantly, each of these theoretical paradigms has very interesting connections with other areas of mathematics. For example, approximation, as we will shortly see, is related to nonlinear approximation. And in fact, it's also related to the problem of controllability, which is a very important problem in control theory. And from optimization point of view, you might have heard from previous talks and also subsequent talks, the connection between this training problem and optimal control, maximum principle, Hamilton-Jacobi equations, and related concepts. And more recently, there's a lot more work on the generalization aspects dealing with like mean field limits and also gamma convergence of numerical methods, okay, which again draws connections between seemingly disparate fields of study. Okay, so in this talk, I'm going to focus on the approximation work, which is surprisingly little studied, but it has some interesting aspects that one can talk about. So what is the problem of approximation? So the basic problem of approximation, as I said, is how big the hypothesis space is. So to frame it in terms of a mathematical question, we can say, given any target function f star, so this is my ground truth, and some epsilon, which is the tolerance, okay, does there always exist a function f tilde belonging to my hypothesis space such that the distance is smaller than epsilon? Okay, so in some sense, can we arbitrarily approximate any target function arbitrarily well, say? If the answer is yes, usually we say that H possesses the universal approximation property, okay? So a remark is that, of course, to have a universal approximation property does not mean that the f star must be contained in H, okay? So this is an important point. So f star may be outside, but if f star belongs to the H closure under some norm, then you also have this universal approximation property under that norm. Okay, so this will become an important point later on. Okay, so our goal is to study the approximation question when it comes to this dynamical systems approach to deep learning. So one may ask, okay, how can dynamics help approximate functions? Now, I think it's best to see such animations, and many of you might have seen or made such animations before. So here we have on the left a data set, okay, with belonging to two different classes. So you can think of as a binary classification problem where each color signifies its own class. So you can see that on this group of points in 2 dimensions, this is not linearly separable, right? You cannot draw a line and separate these 2 classes easily. So what we can do is to try to construct an ODE, okay, such that we apply this dynamical system to each of these points. So you apply the same dynamical system with initial condition equal to each of these points and see what the flow does. Okay, so we have constructed this dynamical system, and then we'll apply it to all these points and see what happens. Okay, so when we evolve in time the dynamical system, these points get rearranged in space. Okay, they are being transformed and rearranged, and at the very end, when the time big T is equal to 4, you have a very nicely, easily separable data set. Okay, so we can classify this entire data set after evolution with a very simple classifier at the end. So this is just a linear classifier. Okay, so what does this really tell us is that the role of the dynamical system, or you can think of it as a continuous time idealization of this deep ResNet, is to somehow rearrange the domain or transform the domain so that difficult to solve classification problem or regression problem becomes much simpler to solve. Okay, so in other words, how does flow maps or flows of dynamical system help to approximate functions? Let's put that into some more concrete mathematics. So we have some input x, okay, and it gets mapped to y through some target f star. So this is something that we don't know. And the dynamical system approach sort of approximated in the following manner. So we take x and we set it to be the initial condition of some dynamical system, right? So some ODE. And then we evolve this ODE up to big time t to get a transformed version, okay, of this original input. And then to match output dimensions, we have to apply a further very simple function g so that we make a prediction y hat. Okay, so this is what we did just now, where this sort of rearranged the domain, and this just is a simple classifier. So we're going to call the family of transformations induced by such flow maps to be the transformational family for the obvious reason. It transforms the domain. And this is a terminal family, which is the last layer. You can think of the last classification or regression layer you apply so that you have the right output dimensions. And if you compose this together, you actually get the target function. You get the approximate to the target function, okay? So to put this precisely, our formulation will be, we have a target function f that maps some RD to RM, where this is the input dimension, this is the output dimension, okay? So we embed the input and output space in these. And then we define some dynamics. Okay, so I'm going to write the dynamics in a more compact form. So this dynamics is the ODE, whose forcing function is time dependent, and they are chosen from a family of functions f. So a curly f is just a family of functions. Okay, a family of functions. And for example, in the simplest case of fully connected neural networks, and you can think of a family of functions like that. Okay, so for each time, I'm going to take a look at all this. This whole family, I'm going to pick one member, and each time I can pick a different member in this family. Okay, so this control family somehow controls the dynamics of this system. Okay, and its complexity will affect the complexity of this dynamics. Okay, so with the control family, we actually induce this so-called transformational family. So transformation family, we call it curly phi, is just the family of flow maps. Okay, so this is the initial condition mapping to the terminal condition. So this is a flow map of this dynamical system where ft can take any value in f. Okay, so this is a set of functions from RD to RD that represent all possible transformations of the domain you can generate from your flow. And then, of course, we need a terminal family, which we'll call it curly G, that maps the output dimensions, input dimensions RD to the output dimensions RM. Okay, so this family is usually very simple. For example, we can consider a linear family. Okay, so this is just X and projected to WX, where W is the obvious dimensions. Okay, so the approximation problem phrase in this dynamical systems framework is basically the following. We have to define a dynamical systems hypothesis space, which is simply the composition of a function G in the terminal family. So this is the last layer, composed with some transformational function from the transformation family. Okay, so this is the family generated by the flow. And often when we talk about density problems or like approximation problems, we can say we can allow for arbitrary depth of the system. So we can take a union over all possible t, or all possible finite t, and consider this entire hypothesis space made from these flow maps. Okay, so this H, which depends on both my control family F, how much freedom I have in my dynamics, and my terminal family G, which is typically simple. Okay, and our goal is to study this object in terms of its density or its approximation property. Okay, so the key question we want to answer in this talk is what conditions on this F and G are sufficient to induce the universal approximation property on this H. Okay, so the justifying why we can use this kind of ODE framework to understand, or at least to idealize deep learning to study some of its properties. Okay, so here I want to bring some your attention to an interesting point, is that this transformation family induced by flow maps or ordinary differential equations are definitely not arbitrary functions. Okay, so a basic observation from a theory of ODEs tell us that each phi, okay, so this phi in this transformation family must satisfy some conditions. The first one is that it is a homeomorphism. Okay, so it's a bijection that, and its inverse is actually continuous. Both it and itself and the inverse is continuous. Why is that the case? Well, because you can just take this ODE and reverse it in time, and you can have at least in continuous time, you have a well-defined inverse, and its inverse is also continuous. And moreover, there is another further restriction in the sense that this map must be orientation preserving. So you can think of orientation preserving as saying that my Jacobian of my mapping is positive definite everywhere. Okay. The reason why I say think is because this map need not be differentiable, well, at least not differentiable everywhere. So there's a way to also define it without this differentiability requirement. But to think about it, you can just think about the fact that it's positive definite. Okay. So what does that really mean? If that doesn't paint a geometrical picture, we can take a look at one dimension to see what that means. Okay. So in one dimension, orientation preserving homeomorphisms are just increasing functions. Okay, so they are invertible, and the orientation preserving, because the Jacobian, which is the derivative here, is positive, right? So that means it's increasing. Now, why is this restriction present? Well, the following is actually a direct consequence of existence and uniqueness of ODE solutions. Okay, so the proposition here is very well known in theory of ODEs, is that the flow map of ODE must be increasing. Okay, so to see why that is the case, you can just take a look at these two pictures. So in each of these curves, I'm just following the trajectory in one dimension of this point x and x prime and x double prime. There's three different points as it evolves through some arbitrary dynamical system. Okay, so it's some arbitrary dynamical system. This is the path. Now, my claim is that these paths will not cross. Okay, why is that the case? Suppose that they cross, okay? So here, these two paths actually cross. Then I'm gonna take a look at this point, x hat. I forget about everything here, and I just look at these two paths. You can see that these two paths are both from x hat, right? But they are different paths. And this actually violates the fact that the solution is unique, okay? They are different. And similarly, the backwards, okay, they are also different. The backward uniqueness also holds by symmetry in time. So they cannot cross, okay? So if it cannot cross, all these paths must be in the first case, okay? They are like not parallel, but they cannot cross each other. If they cannot cross each other, then this function here must be increasing, because if x prime is greater than x, then phi x prime is going to be greater than phi x, okay? Because they cannot cross, so the order is preserved. So in other words, in one dimension, there's a topological constraint that this flow maps actually possess, okay? So why am I talking about that? It's because this then brings the interesting question. So if you look at our hypothesis space, okay? So this is our hypothesis space. And this outer circle is all the set of functions where is G, which is can be written as G, which is terminal family. You can just think of as a linear function, composed with an orientation preserving homeomorphism. Okay, so what I've shown before is that this H is contained in this circle. Okay, because each of this, each of the transformation that you can generate using a ODE must be OP homeomorphism. Okay, orientation preserving homeomorphism. So clearly, this do not include all functions. For example, I can have f star that is definitely not a linear function composed with an orientation preserving homeomorphism. So f star, so there's no way that this function is going to contain all functions you can think of. So in other words, it is easy to see that H has limited representation ability. Okay, you cannot represent arbitrary functions. However, does this restrict its approximation abilities? Now that's a different question. It turns out that the answer actually depends on dimension. Okay, so we have two cases. In dimension 1, true, it also affects its approximation property. Not every function can be approximated. Okay, it means not every function lies in its closure. But in dimensions greater than 2, okay, the closure, at least the closure in the sense we'll talk about later on, will contain all continuous functions. And so this is the point that is a useful distinction to have, is that this closure can be very much bigger than the original set. So this point, the fact that this H possesses some very limiting structure does not stop one from being able to approximate things. Okay. Okay, so with that said, I will go on to present the approximation results for this approximation problem. So to state the results, we need to have some definitions. I will just sort of run through the definitions so you can understand what the theorem says, and then I'll maybe, if I have time, I'll talk about why these definitions are made or these assumptions are made. Okay, so the first definition we want to introduce is that a concept of a well function. Okay, so what is a well function? Let me just take a look at the picture and then you look at the words. A well function basically is a function where there's a convex set, okay, on which bounded convex set on which this function is going to be 0, and outside of it, this function is never 0. Okay, so you can think of this first one example. This is my convex set, which is an interval, and on it equals 0, and everything else is non-zero. Okay, so this sort of the shape of a well, so we call it a well function. But of course, this well function doesn't have to be like this. It can be pointing in arbitrary manners or curved. It doesn't matter. All these are well functions. Okay. So of course, we can generalize the concept of well functions to vector value functions in an obvious way. Okay, so this is the first definition to keep in mind. And the second definition is the restricted affine invariance. So this is really a weaker version of affine invariance. So what is affine invariance? It just means that if you take tilde f to be, this curly f to be any collection of functions from Rd to Rd, say, and we say that f is like affine invariant. If you apply any affine transformation like that, it still stays in f. Okay, so here we have a much weaker version of that. We only need f to be invariant under some specific transformations. For example, any vector b, which is translation, and also multiplication by certain diagonal matrices satisfying various constraints. So this is a very weak assumption. Okay, so with these two conditions, we can now state our main approximation theorem. Okay, so the approximation theorem basically says for any continuous function, okay, if we verify these three conditions for the control family and the terminal family, then we have universal approximation in LP. Okay, so the first condition is a technical condition, which basically says that the range of G, okay, you must have some function, terminal layer G must have range that's big enough. Okay, so we can cover the target function, which is usually trivial to satisfy because very often if you take G to be a linear function that's surjective, okay, then this is trivial because G, the range of G is just the entire space. Okay, and the second condition is that the control family, so the family that controls our dynamics, if you take the convex hull and takes its closure, then it contains a well function. Okay, so this is where well functions come in. So this is the second condition. And the third condition is that our control family is restricted affine invariant. Okay, if you verify these three conditions, then you can prove that, then one can deduce that we have a universal approximation property of this family in LP. Okay, so it's in fact LP local, so it's every compact set. Okay, and so I will say a few words about what each of these mean. So the first condition, as I already said, is a covering condition because the range of this G composed phi is contained in G, so G cannot be too small. But usually this is trivial to satisfy. So what do the other conditions do? In particular, what do well functions do? Now I want to just have a cartoon to illustrate the idea of the proof, at least one part of the proof, is that if you consider a well function like that, and you consider a dynamics driven by this well function, then you can have some interesting phenomena. So recall, what do we really want the dynamics to do? As we see from the example of the GIF before, we wanted to essentially, if you want to have the universal approximation property, you need to be able to rearrange the space in essentially arbitrary manner. Okay, so how do we rearrange things using dynamics? Well, a well function is very good at that, because if you apply this x dot equals to h, where h is a well function, then you can see if my particle or my state is inside the well, it doesn't move, okay, because it's zero. The right hand side is zero, and if it's outside, it can move. Okay, so for example, here you move to the right, here you get attracted to the well, this gets repelled to the well, and because of affine invariance, we can shift this well around and we can negate its signs, that we can essentially arbitrarily rearrange this space. Okay, so this is a one-dimensional version of the argument. Of course, in general, you need a higher dimensional argument. But that is just of one part of the proof. Of course, this is not the entire thing, because we did not assume that our control family contains a well function. We only assume that its convex Hall contains this function. Okay, so there's additional results that we need to establish before we can pass to this general case. Okay, but nevertheless, that's just a taste of why this sort of results will hold. Okay, so just to give an example, here our approximation result is quite unlike a lot of results you see in approximation theory of neural networks. It's a sufficient condition. We didn't assume that the control family is any architecture per se, but we just say that if we have three conditions that you can verify, then you have the universal approximation property. Okay, so that's the first observation. And this allows us to really apply this theorem to a lot of different architectures. The first one, the usual ReLU architecture, is trivially satisfied because ReLU function has this well built into them. But other activations you can also show them. And in fact, even some block structures that you can also show. Okay, so that's the first observation. The second observation is that, again, these families, they are not big. Okay, so these control families, the width of this neural network is finite. Okay, it just have to be greater than or equal to d. It doesn't have to go, to infinity. So all of the computation of the approximation power actually arises from the act of composition. Okay. All right. So I said something about higher dimensions. So in one dimension, it turns out that this result is not true, in that in the one-dimensional case, there are functions we cannot approximate even in LP. This is because of this topological issue that we discussed before. But however, what we can actually prove in one dimension is the next best thing. Is that one dimension, all the results that we said before holds under the same conditions, with the additional assumption that our target function is increasing. Okay, so it's the orientation preserving homomorphism. Well, then we can approximate. Okay. So I'll end off this talk with some discussions or implications. So the first one is that, very importantly, okay, so the fact that this flow maps have some topological constraint in terms of this homomorphism and orientation preserving property does not really constrain its approximation properties in general. And in previous work, uses a lot of these counter examples where you have OP the functions that are not OP homomorphism, and say that you cannot actually represent them by flow maps. But these are not examples that prevents approximation. So that's the key distinction I want to make here. And here again, I already said these approximation results are sufficient conditions, that they don't rely on explicit architectures, and the requirements on F and G are quite weak. Okay, so prior work, I think this work, they studied this approximation capabilities of such dynamical systems, but there it was required that this F control family itself is a universal approximation class, which we do not assume here. And I think this is an important point, because you want the approximation power to come from composition, not from the power of each of the controls in the first place. Okay, and finally, I think this is an important point, is that the universal approximation properties in continuous time implies immediately discrete time density results, UAP in discrete time, as long as the discretization is convergent. Okay, so this is a basic result from numerical analysis. And of course, we know that residual network, you can think of it as Euler discretization, forward Euler discretization of this continuous dynamical system. But then again, a continuous time result will imply that any convergent discretization will have the same universal approximation property. Okay, which is another interesting point that you can deduce from a continuous time approach. So here's a quick summary of the results here. We started with this deep neural network, okay, the residual net. And then we did a continuum idealization of the dynamical system. And then we discussed the problem approximation. And we realized that this problem actually belongs to a class of problems known as, you can think of them as approximation of functions by composition, okay, of two classes of functions, G, which is very simple, and phi, which is some flow, okay? So I want to just remark that, interestingly, in the case of linear approximation and nonlinear approximation, you can also think of them in this framework, okay? We talk about a little bit about this in the paper, and you can contrast the case here that's different from before. And okay, so from here we have deduced some sufficient conditions for UAP, universal approximation property of full maps, and we can then link back to the original setting of discrete residual networks by any convergent discretization. Okay, so the advantage is that we obtain much more general results this way. Of course, you can do direct approaches, and this is most of the existing results in neural network approximation. But in this way, you gain some additional insight and additional flexibility, I think is important to highlight. Okay, so some future work, we can try to study the approximation rates of various things, which I didn't mention, but we did talk about a little bit in the paper. And of course, we can talk about necessary conditions for optimality, necessary conditions for approximation. And this is maybe of purely mathematical interest. And also we can discuss, can we approximate some functions of symmetry, for example, CNs? We have some results in this direction coming up soon. So with that said, I've come to the end of my talk. So I will take any questions. So I have the last slide on broader picture, but I don't think I have time to discuss that. So here's the reference for the paper I talked about, and there's some other aspects of mainly in the optimal control setting. Okay, so thank you very much, and I'll take any questions.
Great, thank you very much for the talk. It was very interesting. We are a little bit over time. If you don't mind, we'll shift the questions to after the session. We'll have the chat, then we'll have the session open for a little longer. So any questions come up can be afterwards. Maybe if we can switch to the next speaker, Bin Dong, immediately.